Chris. And just before I get started, I just want to check how audio is in the screen share.
Audio is good. Screen share is also good.
All right, sounds good. So as Bryce just said, my name's Elliot Ronaghan. I'm the lead performance engineer for Chapel at HPE. And the core of what I want to talk to you about today is aggregation in Chapel and how our asynchronous task-based runtime enables an efficient and elegant implementation. And I kind of want to go through just Chapel by example if you're not familiar with it, and then we'll delve into kind of the background and context and motivation for Chapel, look at some of the base language features that are used to implement aggregation, and then look at aggregation itself and its use in some user applications. So delving right into it, so if you're not familiar with Chapel, it's a modern parallel programming language. So it's portable and scalable. And by that, we mean it's designed to run on anything from, say, Raspberry Pi to your laptop to desktop to clusters, clouds, and the largest supercomputers from HPE and other vendors. And it's open source and collaborative. So it's developed on GitHub under an Apache 2.0 license. And we collaborate with members of academia, industry, and just kind of the general user community as well to develop Chapel. The high-level goals for Chapel are to support general purpose parallel programming and to make parallel programming, particularly at scale, far more productive. And to kind of show what we mean by productivity, I want to go into kind of an example application or an example benchmark to see what this looks like. And so we're going to start with HPC Challenge Random Access, or RA, also known as GUPS. And kind of the key data structure you have for this is a big distributed table that's seen here kind of pictorially. You have the yellow, which describes the memory, and then the vertical red lines represent different compute nodes. So we have our big distributed array T, and we have some number of updates we're going to perform to this table. And then in parallel, we're going to update random elements of the distributed array with random values. And in this particular case, we can see that, for example, node 0 is updating memory that lives on node 0. Node 2 is updating memory that lives on node 0 as well then. And you can see that node 1 and node 4 here have some conflicting updates. And so for this particular talk, we're going to think about this in terms of lossless updates. So we're going to be using atomics. And in Chapel, the declarations for these two data structures would look something like variable T is an array declared over a block distributed domain, where a domain is just a description of the index set. So we have a block distributed array of atomic integers, and then our updates is just a block distributed domain over the number of updates that we're going to be performing. So this is kind of the description of the problem. Taking a step back from Chapel, if we look at what this looks like in MPI, it's a significant amount of code, and I'm definitely not expecting you to understand or even read all of the code that's here. Kind of the highlights of this slide are just that in blue we have comments, in red we have the MPI or kind of the communication, and then in black is just kind of the regular serial straight line code. And what I want to highlight here then is this is the equivalent Chapel kernel. And so kind of the basis of what we have here is a for all, which is a data parallel loop. So we have a for all over the updates domain and this random access stream, which is going to yield our random indices. And then we have T at our random index, X or the random value. And then from the MPI code, what we have is the following comment kind of above all of the more complicated implementation. So it just says, perform the updates to the main table. The scalar equivalent of this is for I and some number of updates, compute your random index, and then the table at the random index, X or the random value. And so really what I want to highlight here is, the Chapel kernel is able to basically describe what's happening in the same amount of space that the MPI comment is able to. And here, I think this kind of shows what we're talking about when we talk about kind of productivity and improving the productivity of parallel programming, right? We want to be able to describe the core computation and have that be visible and kind of concise and expressive in the source code itself. And then moving on to kind of the performance of this. So this graph here is a performance scalability graph. So higher is better, and to the right is more nodes, up to 256 nodes. And this is on a Cray XC. And I think at 256 nodes, that's 9,000 cores. And for this particular benchmark, we see that MPI tops off at around just under 2 GUPS at 256 nodes, and Chapel is able to achieve 12 GUPS here. And for this particular benchmark, it's a really natural fit for Chapel, and we're able to map this down to network atomics on the Cray XC hardware. So it's a particularly good fit and one that we can optimize really well for. And if we come back to kind of the core kernel, this for all in the number of updates and then indexing into the array, and we kind of break down what this gets lowered into or kind of how this actually maps to hardware. What we see here is we have this coforall over the target locales, basically the nodes that the updates array is declared over. So we're going to have a concurrent loop that spawns a task on each remote node. We're going to have a nested concurrent loop that's going to create a task per core. So this kind of gives us an SPMD sort of region. And then here we have a serial loop to compute each task chunk of the number of updates. And if we actually just generated this type of code, the XOR that we have here is ordered by default to adhere to Chapel's member consistency model. And by default, we implement ordered operations as blocking ones. So kind of you have the network round trip wait for this. And so if we just generate that code, then this is the type of performance that we would have. And this is the performance we had back in 2018. And the key things here is we still have the MPI line in green, and then in blue, we have two different Chapel versions. And the exact performance for the versions doesn't matter too much, just here that when we do ordered operations, we're getting performance that's closer to MPI and isn't as spread as we saw in the original graph. And what I want to come back to in the code then is when we're just doing kind of the naive lowering and using ordered operations, that's the type of performance we see. But looking at the source code, right, this is a data parallel loop. And we can see that there's no data dependencies between iterations. So there's no reason to perform these high latency atomic XORs serially. And so we added a compiler optimization to rewrite this so that instead of doing blocking XOR ordered XORs, we can do them in an unordered or non-blocking fashion. And then the compiler can insert an appropriate fence to make sure that the program still adheres to the memory consistency model. And it was this XOR, kind of the unordered XOR transformation that allows us to get the performance that far exceeds the MPI code. And going through this, really what I want to call out is that, we had this really high level and kind of, productive, if you will, Chapel kernel compared to this, pretty dense and explicit MPI code. And it's interesting to think about, what would it take for a compiler to optimize the MPI code in order to have competitive performance? And I really just don't think that's tenable. So much of the MPI code is describing exactly how to do communication rather than kind of the high level algorithm. And it's really hard to imagine that you could write an optimizing compiler to make those transformations. And you can imagine, well, a user could rewrite, the MPI code to use Cray's network atomics efficiently, but that's going to be a significant effort and it's not going to be portable. And so here again, just the point I'm trying to make is that a high level language can enable more productive programming that can still allow you to get good performance and can map efficiently down to hardware. And so here, that was just kind of the intro to Chapel by example. The rest of the talk, we're going to go through the motivation and context for Chapel, highlight some of the tasking and locality features which are used to implement aggregators, and then get into aggregators themselves and their use in a user application called Arcuda. And one of the questions we get asked a lot, or at least got asked a lot historically, is why bother creating a new language at all? And kind of the main theme that we tend to answer with is that because we think parallel programmers deserve better. And the state of the art for HPC tends to be a mismatch of libraries, pragmas, and extensions. But parallelism and locality are really first-class concerns that deserve first-class language support. And there's a talk from Kathy Yellock that we reference a lot. This was originally some information she had in a UPC talk years and years ago, and then kind of brought back for a keynote she gave at the Chapel Users Workshop in 2018. And I really like a lot of the bullets that this goes through. So it's basically why consider a new language at all? And the top bullet here is if you need syntax to improve programmer productivity, then you really need a new language. And I think we see that for things like RA, where Chapel is able to very concisely and clearly describe the problem space. And then if you can have static analysis that can help with correctness, then you need a front-end compiler. And then if you have optimizations that are needed to get better performance or to map more effectively to target hardware, then you need a compiler backend. And I think we see this in the RA example where we're able to take kind of implicitly ordered code and have compiler transformations to make that unordered based on the analysis. And then last bullet is the one that I find the most interesting. And it's in the sense that languages define what's easy and what's hard. And I think that was also really clear in the RA example. Like RA and this kind of fine-grained distributed COM is not a good fit for MPI. So you can see that in the code, it's hard to implement. You kind of have to restrict and conflate how you use MP and IDER to get it to work. But it's a very natural thing to do in Chapel. So the language defines what makes it easy and what makes things hard. And these are kind of the main reasons that we think about for why add a new language. We want to have clear syntax, and we want to be able to make common things in HPC easy. And we don't think that any existing languages really fit these desires. And I mentioned too that this is a question that we used to get asked more. I think as kind of other mainstream languages have become more prolific, this question gets asked less and less. Like people have seen the success of Rust or Swift or Go in their respective domains, and it makes more sense for why you might want a language. And in particular, why HPC and just kind of general purpose parallel programming could use a new language to make things that were once difficult easy. And when we think about what we're trying to achieve with Chapel, there's kind of a combination of features from other languages that we're striving to bring in. So we talk about this in terms of being as programmable as Python, where really we're talking about kind of the readability and expressiveness of Python. But we still want to be fast. We want to be as fast as, say, C or Fortran, and as scalable as existing HPC technologies like MPI or SHMEM or UPC, and as portable as C in terms of being able to run, kind of on as much hardware as you can. Now, C is insanely portable. We want to actually match that, but just kind of the general sense of we don't want to be vendor locked or anything. We want to be able to run on basically any parallel hardware that you have access to. And when we talk about being as flexible as C++, this is more in terms of being able to do generic programming and kind of the template meta programming that you would have there. And this last bullet, we want Chapel to be as fun as whatever your favorite programming language is. This one I think usually gets a couple chuckles at talks, but I actually think it's really important. And I think it's important because, I think a lot of us, myself included, got into programming because it was fun and exciting. And I think that's really lost in the day-to-day of HPC programming. And so for me, I'm kind of like a diehard C programmer. Most of my time is spent in really low-level runtime code, talking to the hardware. And the end result can be satisfying and enjoyable, but like kind of the day-to-day programming isn't particularly fun. What I have a lot of fun with is writing a small little Python scripts to do some testing or something like that. And what I found is that Chapel kind of brings that same level of joy and ease to HPC programming. And I really think this is not one to be underestimated because it's what attracts kind of new talent to HPC. And you've already seen this, but Chapel benchmarks then tend to be pretty concise, clear, and competitive. So in the top here, we have Stream Triad, which is kind of like the hello world for HPC, kind of one of the most simplistic, embarrassingly parallel or pleasingly parallel applications or benchmarks you can write. And here the code for Chapel is concise, and we see that performance is competitive with MPI plus OpenMP on the right here. And then the second one is for HPC Challenge RA, which we already saw. Again, kind of a clear, concise kernel with performance that is competitive, or in this case, beats MPI. But benchmarks aren't the be-all end-all, right? We really care about what are users doing with Chapel. And especially over the last 2 to 3 years, we've seen a pretty huge increase in the number of users writing substantial amounts of Chapel code. So some of them are listed here. 2 that I want to call out today. In the top left, we have Champs, which is a 3D unstructured CFD. And this is, I think, one of the largest applications using Chapel. I think they're up to 120,000 lines of Chapel code. And then the second one I want to call out here is Arcuda, which is effectively a NumPy and Python front end that's backed by Chapel for the distributed and scalable performance. This is originally from Mike Merrill and Bill Roos at the US Department of Defense, and is around 22,000 lines of code here. And Arcuda has really benefited from aggregators in Chapel. And so we'll be talking about this later. This is kind of the user application I want to focus on when we get to aggregators. And again, here, just at the end of the day, what users are able to accomplish with the languages is what's most important to us. And coming back to kind of the language itself, so we have what we describe as a multi-resolution philosophy in Chapel. So we want users to be able to write kind of the high-level abstractions that we showed for the RA example. But then if they need to or they want to, for ease of expressiveness, we want users to be able to drop down to lower levels. And so this whole array index gather, this destination equals source at indices, is kind of what we think of as kind of the highest level of abstraction. And if users want to, for better control or performance, they can drop to lower levels. So here, instead of doing whole array index gathers, we're doing a data parallel loop. So a for all over the destination and indices, and then your destination at a particular index equals your source at your random index here. And you can continue to drop lower, so you can get kind of the SPMD sort of style code that we looked at with how RA was lowered. So here we have a cof-roll over the target locales of the destination, and then migrating execution of that locale, and then a data parallel loop within that node. And then you can go lower still, where kind of the lowest level would be calling out to C or CUDA or MPI or whatever other programming paradigm you want there. And a really important note here is that Chapel builds its higher level abstractions in terms of these lower level ones to guarantee compatibility and composability. So for all of these examples, like the compiler does lower that whole array index gather into the for all, which actually is implemented under the covers with kind of the nested co-for-alls. And this is really important for compatibility and composability, but then it also means that if users need to go to lower or higher levels, they're not going to see a big performance cliff or anything like that. And when we think about this more pictorially, we kind of view like domain maps or the distributed arrays and domains that make them up as kind of the highest level of abstraction. Below that, you have the data parallelism, like the for-alls. And then kind of the lowest levels of the Chapel stack here, kind of the task parallelism, the base language, and the locality control are what we tend to think of as the lower level features that those higher level things are then implemented in. And for today, we're going to be focusing on kind of the task parallelism and the locality control features because those are the things that are important for implementing aggregators in Chapel. So I want to go through some of those just to give some context for what this looks like in code. And then in the section after this, we'll get into their use in aggregators. And before I get too into that, I wanted to talk a little bit more about kind of what are Chapel tasks and, kind of what like how you would define them. And, kind of the way that we think about Chapel tasks is that they are asynchronous in the sense that they're launched dynamically, they're managed by a runtime, and they don't have a predetermined start or end conditions. But, I think a lot of asynchronous many task platforms also have kind of the graph of dependencies, and that's not an aspect that we have in Chapel, but we still think that they're kind of asynchronous. And this asynchronicity gives expressiveness benefits in that, basically any parallel pattern can be expressed. And in practice, we'll see that many patterns use groups of tasks doing similar things. So we saw that in kind of the co-for-alls before. And this asynchronous nature can improve performance by spreading out network load and avoiding synchronization bottlenecks that you would see in a traditional kind of bulk synchronous PGAS sort of language. And the aggregators, and we'll see this later, but the aggregators really benefit highly from this asynchronous nature and the ability to not have to synchronize with other tasks. So moving on to some of the Chapel features. So locales are things that can run tasks and store variables. And then you can think of this as a compute node in a parallel system. And so when you're executing a program, you'll specify the number of tasks like you would specify the number of ranks for MPI. So here we're running a program with 4 locales, and this is going to result in an execution that has a locales array with 4 elements for locale 0 through locale 3, and basically the 4 compute nodes here. And a really important distinction between kind of traditional PGAS is that user code starts running on a single task on locale 0. And so this is kind of a break from kind of traditional SBMD programming, and we kind of refer to this as kind of a post-SBMD model. And so looking at some code here, so this is a task parallel hello world. And what we're going to be doing in this snippet is we're going to have some number of tasks, and each of those tasks is going to write out some identifying information. And we use a concept of here, which refers to the current locale that you're currently running on, basically get information about the current node. And here, this here.numpuse is asking how many processing units, kind of an abstraction or a generalization of how many cores does my node have. And so we're going to have basically a task per core, and then we're going to write out the name of the particular node we're running on. And this co-for-all, which we've seen before, this is a concurrent loop that's going to create a task per iteration. So here we're going to create num tasks. And if we look at the output from this, so we're going to run this, and we're going to see on a 4-core system, we're going to have 4 tasks running. And because we haven't done anything to synchronize these are going to execute in arbitrary order. So here we see that task 1 prints out first, and then task 4. And a really important thing to note here is that so far this is a shared memory program. There's nothing in this that refers to remote locales either explicitly or implicitly. And in Chapel, we have distinct concepts for parallelism and locality because we believe that they're both, kind of distinct and important to be able to program to separately. So if we want to look at a distributed hello world, then it's a pretty simple change that we need here. So we're going to add a co-for-all over the locales array, and then migrate execution to a particular locale. So this co-for-all is the same as other co-for-alls. We're going to create a task per locale. And then here, we're logically going to migrate that task to a remote locale or a remote node. And it's kind of a logical migration. In reality, we're not going to create a task only to move it. We're just going to directly create the remote task. And then the loop we had before is the same as before. multiple tasks on a given locale or node are going to print the messages. And if we look at the output from this, in addition to kind of the tasks within a node being interleaved, we also have interleaving at the node granularity. So here node 32 prints out twice, then node 34, then node 32 again. And I think I said this already, but we tend to think of this as kind of a post-SPMD execution model. So in a traditional PGAS language, you're going to have a very, SPMD programming model with RL, PEs, or ranks, or threads, or whatever, start by executing main. And as we've seen already, a single task in Chapel starts executing main on locale 0, and then any additional parallelism, either local or distributed, is introduced from there. So you have kind of a traditional fork join mechanism. And this is something that is, I'll say it seems obvious to people coming from kind of traditional programming models. Like if you're talking to a Python programmer or, whatever, they wouldn't understand why you would do anything other than this. And, it's kind of a big mental model to switch to SPMD. So I think this has pretty big productivity benefits. And coming back to then kind of the partition global address space, which is another one of, kind of the more unique things about Chapel in the HPC space. So I want to give an example of what this looks like with some on clauses. And these are some concepts that we've seen already, but delving into a little more detail. So we have these variable declared here. We have a constant verbose, and we have two variables, total and done. And then if we think about how this maps to the locale, so the locale is basically your compute node. So we have some memory on this node. It's storing verbose, total, and done in its local memory. And then if we have an on clause to migrate the task's execution, in the snippet, we're going to say, okay, if we're not done and verbosity is on, we're going to write something out. And then just if we're not done, we're going to add some total, or we're going to add some computation to our running total. And here what's happening under the covers is we have a logical migration of this task to locale 1. And then the memory that it's referring to, so it'll make a copy of verbose and done. It can do this because verbose is constant, so we know it can't change. And done, the compiler is able to analyze and see that according to the memory consistency model, nothing here is changing done. So it's also safe to send along with the argument bundle that makes up the on statement or the active message that's used to implement it under the covers. But then we know that total is changed in this loop, so we can't make a copy of total. We actually have to modify the original one. And so here we'll do something like an RDMA get to acquire it, add our local value, and then an RDMA put to store the value back to locale 0. And here the really important thing that I think is worth noting is that we tend to think of this partition global address space we have in Chapel as also kind of post-SPMD in nature. And kind of traditional PGAS or traditional SPMD is kind of the nature of I have a variable named X, so you must have one in your node too, so therefore I can refer to it. And then sometimes this also requires a symmetric heap. But in Chapel, you can access any variable that's in your lexical scope, whether it's local or remote, and then it's up to the compiler and runtime to ensure that you can actually get access to that. And here, this is another case where I think these two things combine, kind of the post-SPMD execution model and the post-SPMD global address space, make Chapel programming feel much more natural or much more kind of similar to traditional programming models that you would use on a single node. And so it feels, it feels easier for people coming from outside of HPC to kind of ramp up on this. And then bringing some of these concepts together. So here I want to look at kind of just bulk communication in Chapel, combining some of the things that we've already talked about. And bulk communication is kind of one of the underlying things used for aggregation. And so we'll see why this is important later. So in this example, we have an array buff that's declared on locale 0. We're going to migrate execution to locale 0. And then here, since buff is lexically available in our scope, we can refer to it. And so here we're going to allocate space for a local buffer, and then we're going to do a logical get from locale 0 to locale 1, or I guess locale 1 from locale, to locale 1 from locale 0. We're going to process the data, and then we're going to do a logical put from locale 1 back to locale 0. And again, here, just the ability to do these on statements are kind of these remote procedure calls, and the ability to refer to things within your lexical scope are really important building blocks in Chapel that enable things like aggregation. And so moving on to aggregators themselves, and kind of the intro for this is we're going to look at aggregators, but we're also going to look at them in the context of Bale, where Bale is a collection of mini applications and aggregation libraries. It has a bunch of mini applications, and Chapel has a couple ports of those, including one we're going to focus on called Index Gather. And we on the Chapel team use Bale to evaluate kind of the productivity of our aggregators and then compare performance to SHMEM. And there's a snippet from the open source Bale repo that I really like, where they describe Bale as a vehicle for discussion on programmer productivity. And they describe the Bale effort as an attempt to demonstrate some challenges of implementing interesting, or in their case, really irregular and fine-grained distributed scalable applications, and then an attempt to demonstrate an approach, namely aggregation libraries, to achieve high performance on inter-node communication, and an attempt to explore concepts that make it easier to write, maintain, and get top performance from such parallel applications. And I think one of my favorite lines from the README in this repo is that we, the Bale developers, use Bale to evolve our thinking on parallel programming in the effort to make parallel programming easier, more productive, and more fun. And yes, we think making it fun is a worthy goal. And here I think this is interesting because a lot of the goals of Bale are the same goals that we have in Chapel. We want to make parallel programming significantly easier, more productive, and kind of more fun, right? And it's interesting to me here because the Bale effort is really started by kind of developers who have been doing UPC and SHMEM programming for most of their careers, and they kind of want the same things that we do out of this goal. So I think Bale is a really good fit for us in terms of being able to evaluate the performance and productivity of our applications, and then also have a baseline to compare that against with SHMEM. So focusing on Index Gather, again, kind of one of the core mini applications in Bale. So this is the entire application in Chapel. So we're going to use our block distributed arrays and the random module. We're going to have some number of tasks here, which is basically a task per core. We're going to have some number of updates we're going to perform per task, and then we're going to have some number of entries in our table per task. We're going to declare our distributed domains and arrays here. So we have a distributed array source, which is a block distributed array of integers. And this is the thing we're going to gather from. And then we have our destination and our random indices. So destination is where we're going to store results, and indices is the random indices that we're going to gather from source. And then we'll fill the indices with some random values between 0 and the size of the source array. And then the actual kernel here is this naive index gather. So we're going to have this data parallel for all over the destination and the indices, and we're going to do d equals source at some index. And expanding on kind of the kernel a little bit, as I just mentioned, the destination and indices are distributed arrays, and they have num updates elements, and source is a distributed array with num entries elements. And if we do the kind of the same lowering that we looked at for HPC random access, it's basically the same. We're going to take this data parallel for all. It's actually implemented in terms of nested co-for-alls under the covers. And then we have the serial region within kind of the larger SPMD section. And same as random access, there's no data dependencies, so there's no reason to perform these operations serially. So we can also transform these to use unordered operations. And if we take a look at the performance of this, so this is performance on a Cray XC up to 512 nodes, I think 18,000 cores or so. This is also performance scalability, so higher is better, to the right is more nodes. And the darker blue line that we see at the bottom is the ordered or the non-optimized version. We get up to around 100 gigabytes per second at 512 nodes. And going unordered, we can get up to around, I think, 400 or 450 gigabytes a second. But the important thing to note here is that all of these are still doing fine-grained messages, right? So this is 8-byte gets. And these are things that perform pretty well on the Aries network that's in the Cray XC system. But we know that we can get better performance by making this bandwidth bound instead of latency bound, even on the XC, but in particular on other networks like InfiniBand or commodity networks like Ethernet, where latency is really high, but bandwidth is still pretty decent. And this is really what motivates the need and the desire for aggregators. And so if we take a look at what our aggregator implementation looks like from the end user's perspective, so at the top here, we have the same naive index gather we were looking at before. And in the second box, we have the code transformation that's required to aggregate. And so the changes here is a use to bring in our copy aggregation module. We have the same data parallel loop driving things, but we've added this with clause to create a task private variable ag, which is a source aggregator. And the source aggregator is going to aggregate things that are logically remote or would result in kind of a network get, if you will. And so as to creating a task private variable, so when we think about how this is lowered to the nested coforals, that means kind of each of the inner coforals has its own task, and it doesn't have to synchronize with any other task. And then instead of d equals source of I, we're just doing ag.copy d source of I. And then under the covers, what's happening is as these aggregator buffers fill up, they're going to communicate and do operations with the remote nodes or remote locales, and they'll do this kind of automatically and asynchronously, where there's no kind of coordination or syncing between tasks. Everyone's kind of operating independently. And if we look at the performance of this then, so we have the same graph we did before with the ordered and unordered versions in darker blue and medium blue on the bottom here. And then we see that the aggregated version takes us up to around 1100 gigabytes a second here at 512 nodes. And this again is on a Cray XC, which has good support for fine-grained messages. The performance delta on kind of commodity networks or even InfiniBand networks is larger here, but at the end of the day, we're effectively just bandwidth or network bandwidth bound now instead of being bound by latency. And then in the previous examples, we saw that the compiler can automatically take ordered operations or semantically ordered operations and make them unordered when it can do enough analysis to determine that's safe. And I think that leads to kind of a natural question of, well, can you do that for aggregators too? And we do have we do have a kind of an initial implementation to make that optimization. So the compiler can automatically transform kind of the naive index gather to this aggregated version. And this was developed by Engan on our team in 2021. And it kind of combines all of the analysis that we needed to do the unordered optimization before, along with some new locality optimizations that are locality analysis that's required to see if the optimization is legal. And for me, I think this is an interesting optimization, and it also kind of calls back to, the benefits of having a language and the benefits of having a compiler. Like these are pretty sophisticated transformations and analyses that are needed to prove this is safe, but it ends up being pretty straightforward with the high-level semantics that the user has expressed to us here through the data parallel loop. And this automatic optimization, it's also using the same interface as the user-defined aggregation would be. So the performance of this is the same. And we can see that here with the dark blue line with the triangles overlaps the user aggregation with the lighter square ones here. And so to this point, this has all been, just kind of standalone Chapel performance results, right? And so I said that one of the reasons that we like using Bale is because it allows us to compare to SHMEM. And that's what I want to highlight here. And the graph on this page is small, but we'll look at a bigger one on the next slide. I just want to go through some of the excerpts for what the code looks like here. So at the very top, we have the elegant SHMEM version. And I think this is also pretty intuitive and easy to understand, right? So we're going to have an SPMD SHMEM code. So each PE or rank is going to be doing this. So it's going to do its own updates, and it's going to do a SHMEM get from a random index into its table, into its target or destination. And I think this is, reasonably productive and elegant, but the problem in SHMEM comes from when you want to actually do aggregation. So the Bale library has two primary aggregator libraries called Exstack and Conveyors. Exstack is much more synchronous, and Conveyors attempts to add some asynchrony and some other features. But in both cases, the need to aggregate or the code required to aggregate really obfuscates the original intent of what you're trying to do. And the original intent, again, is just we're trying to do a gather from a distributed array into some target array. And the code's small, so I don't necessarily expect you to be able to read it here, but it's really hard to see in the code that the original kernel was trying to do a gather. You have some complicated things like you have an outer while loop that's checking for global completion, because not only do you need to know if you're done sending updates, you also need to know if anyone else needs you to process updates on their behalf. And then you have code and kind of phases to push the addresses that you want to gather information from, and then exchange that data and then fill up your local buffers. And then at least in the Exstack version, there's barriers here. And again, all I'm trying to get at here is that, the aggregation improves performance a lot, but it really obscures the code and the intent of the code here. And if we compare that to the Chapel version, so we've already seen the kind of the elegant or the intuitive or the naive Chapel version. And we see that with the data parallel for all over the destination and indices. And we know that this can be automatically optimized by the compiler. But even if you couldn't do that, I don't find the manually tuned or the manually aggregated version to be that much worse in terms of code readability. It's the same data parallel loop. We're adding some variables to do aggregation, and we're switching out an assignment for the copy. And then blowing up the performance graph here. So this is still a performance scalability, so higher is better. And we have the same blue lines we did for Chapel before, and what we've added in now is the SHMEM versions. So in this case, we see that Exstack, the dotted green line, performs better than Conveyors in the dashed green line. And this is a case where index gather is a relatively simple kernel. So the synchronous nature of Exstack allows it to have some additional optimizations. But we can see here that the Chapel version is able to outperform them. So we see kind of at the high end at 512 nodes, we see Exstack at around, I think, 800 or 900 gigabytes a second, and Chapel at around 1100. And I think this raises natural questions as to, okay, well, how are we getting this type of performance? And that's what I want to delve into next. And before we kind of delve into the actual, well, how do we get performance? I just want to note that Chapel aggregators are implemented in Chapel code. So we did not add any new language features or compiler optimizations to implement the actual aggregators. There was the change to add the automatic aggregation, but none of that was required for kind of the base implementation. The initial implementation we had only relied on high-level features, and the current version that we use in production, it has some optimized calls to lower-level puts and gets, but it's all user-facing features that we're using here. And so it relies on things that we've already seen, like object-oriented programming with records, initializers and deinitializers, the arrays in Chapel, and some of the global namespace and task local variable things that we've seen in the previous slide. And in terms of the aggregator itself, not really the part that the user uses, but the underlying aggregator. I think the source aggregator has maybe 100 lines of code, and the entire copy aggregation module has around 420. And so this is for the source and destination aggregators and kind of the support code that goes with it. And that code itself is relatively straightforward. This is an excerpt from our initial implementation. And so we have arrays that store the things that we're trying to buffer. So we're buffering the destination addresses and the source addresses, basically the values or the addresses of the values that we want to get and the location that we want to store them in. And what happens when you call that copy routine is we're going to store the addresses in those arrays. And then when it's time to flush, basically when any one of those buffers is full, we're going to come and call this flush routine. And then it's going to allocate a landing spot for the remote source values. We're going to migrate execution over to a remote node. And we're going to do a bulk get of the source addresses. We're going to declare a local array to store the values. And then we'll actually put the values in that array and then do a bulk put back to the original locale. So this is pretty similar to kind of the bulk communication idiom we saw before. The main difference is that we're kind of building up these buffers automatically for the user instead of requiring them to do any of that work themselves. And then it's using kind of the same language concepts that we saw before. So the array assignment, the on statements to migrate execution. And then after all of this is done, once the on statement is done, we're going to store the source values in the original destination addresses that we had buffered. And again, this was the original implementation we had. The optimized implementation is not significantly different. The main things are that instead of allocating each time, we do cached allocations, and instead of doing array assignment, we use some of the lower level put and get features. So these aggregators, I think, allow more flexibility than traditional aggregators. And in the SHMEM versions, we saw that they can require barriers or collectives, and they also tend to assume that everyone is involved in a kind of a quasi lockstep operation. Basically, they're assuming that all ranks in the application are also doing aggregation in order to make progress. But Chapel's post-SBMD nature really relaxes those kind of bulk synchronous constraints in the sense that tasks can communicate with remote locales asynchronously once a buffer is full, and any subset of tasks or locales can utilize aggregators, and they can communicate with the target node without that target node knowing that they're involved. And this is kind of through the on statements and the active messages that make them up. And then coming to the tasking part, so it's user level tasks that really make this implementation efficient. And we use Sandia's Qthreads library as our basis for that. And this ends up being really important because when we're doing these on statements, when buffers are full, this results in potentially thousands or tens of thousands of remote tasks being spawned and run. And so Q-threads and just kind of the user level tasking in general provides us with a couple really important things. One is fast task creation. The other is really fast task switching. And these things combined let us do really efficient kind of communication and computation overlap. So when we're buffering, we're able to send the remote data. While we're sending that data, we'll switch to another task, and maybe that new task is then filling up a buffer for someone else. And then when we do the on statement, same thing, we can yield to another task to allow others to make progress. And this ability to quickly switch between tasks enables latency hiding that is really hard to do in SHMEM. And this is the core reason why we're able to beat the SHMEM implementation, is the ability to hide that communication latency and to be able to do additional computation while that's going on. And then as we've seen, this performance is competitive and even exceeding the kind of performance that we're seeing out of the optimized SHMEM libraries. So the aggregators that we have give clean code, competitive performance and scalability, and didn't require major modifications to the language or compiler. And so, a lot of that kind of sounds too good to be true. So, kind of raises the natural question of, well, what's the catch? And it's not necessarily a catch, but the current aggregators only support these copy style and atomic operations. And ultimately, you really want to be able to support general purpose or arbitrary user-defined aggregation. And in principle, it's really not that different from what we're doing today in terms of the underlying aggregator implementation. The thing that you really want in order to be able to have the user specify arbitrary ways to aggregate and then flush the operations is really first-class functions, though, and Chapel support for that is a bit weak. So for now, we really have the copy style and atomic operations in terms of built-in aggregators. And then a sufficiently advanced user could write their own aggregators. I think I mentioned before, it's really only 100 lines of code per aggregator, but it isn't as trivial as just, kind of specifying a first-class function or a lambda to specify how to aggregate. That said, though, there's definitely a lot of interesting computations that can be written with these copy style aggregators over the atomic ones. And in particular, the user application I want to talk today about is Arcuda. And so focusing on aggregation and Arcuda and just kind of giving some context for what Arcuda is. So kind of the baseline or the problem that the Arcuda developers had originally was that they have HPC scale data that they want to operate on, and they have a ton of Python programmers with access to an HPC system, but no practical HPC experience. So they're trying to figure out how do they leverage all of their Python programmers to get their work done. And so what they ended up with is kind of a client-server model where there's an Arcuda client, which is written in Python, and the users are going to interact with that like they would any kind of normal NumPy or Pandas application through a Jupyter Notebook here. And then behind the scenes, whereas NumPy is usually implemented with a C backend, here it's kind of going to be a Chapel server that's going to do all of the heavy lifting and do the parallel and distributed operations. So Arcuda at its core is a Python library that supports a key subset of the NumPy and Pandas APIs for data science. It uses this kind of client-server model where there's a Python client that looks like NumPy to the end users and a Chapel backend. And we're able to compute massive scale results, multiple terabyte sized arrays. And the really important thing here that was important for them was to be able to compute on those multiple terabyte arrays within the human thought loop. They're doing exploratory data analysis, so they want to be able to do an operation and then have it complete before they get distracted so that they can take a look at the transform data and figure out what's the next operation to do. And this is 22,000 lines of Chapel code. Most of this was written in 2019, although it has been improved since then, in particular in terms of performance. This was originally from Mike Merrill and Bill Roos at the Department of Defense. And like Chapel, Arcuda is open source and available on GitHub. And if you ask the Arcuda developers why they chose Chapel, it's a lot of the same themes that we've been highlighting today. Right? So it's a high-level language with good performance and scalability, and it's close to Pythonic, which allows rapid prototyping, and it doesn't repel Python programmers who look under the hood. So most of the core Arcuda developers are just Python developers, and they've been able to really quickly ramp up and program non-trivial distributed computations using Chapel. And then the portability that I mentioned before too, right? So Chapel ports from laptops to supercomputers, so they do almost all of their development on their laptops, and then only run on the big iron when they're ready to operate on real data. And if we look at the performance of Arcuda, so this is for a gather kernel, which is effectively index gather, but implemented in Arcuda. So this particular graph shows performance of a Cray XC compared to an HPE Apollo system. So kind of the aging XC line compared to a modern Apollo system with HDR100 InfiniBand. And here, all I really want to show is that we see that the modern InfiniBand system has substantial performance benefits over the XC line. And so we have kind of good performance portability to Cray networks and modern InfiniBand systems as well. And in this particular graph, we don't have kind of any reference SHMEM versions. I think there were some system level bugs when we went to gather the information. So no direct comparisons, but here just again, the XC performance that we saw before, and then the Apollo system is able to pretty significantly outperform that. And Gather is not too interesting in Arcuda itself. What's really interesting to them is the ability to do sorts on large amounts of data. Sort tends to be their rate limiting operation for almost all kind of higher level algorithms that they're building. And so here, this graph shows another performance scalability graph for Arcuda's argsort. This is operating on 128 gigabyte 128 gigabyte arrays per node. And this is up to 576 nodes, which I think is around 74,000 cores. And so the 128 gigs on all of those nodes, I think is a total of 72 terabytes of data. And with Arcuda, they're able to sort this in 2.5 minutes for an effective rate of 480 gigs a second. And the rate is good, and I'm definitely no sort expert, but the Arcuda developers indicated this is close to a world record. And the thing that I find more interesting than that is that this is 100 lines of Chapel code to implement the sort. It's a really simple least significant digit radix sort. I think it was ported from Nestle and ported in maybe an afternoon, and then it was another afternoon or another day to switch it from using kind of fine grained operations to using the aggregators. So regardless of kind of the world record standing, we definitely think this is a record for kind of performance per source lines of code, right? You could write significantly more complicated sorts that do much more locality aware sorts of operations, but the implementation complexity and the maintenance complexity of that goes up significantly. So I really think this is a nice kind of demonstration of you can have high level productive code that still has excellent performance and excellent scalability. And then here, so this is also on the HPE Apollo system, so that's InfiniBand. I can't share kind of official results yet, but as we're thinking about moving towards exascale machines, and the first exascale machines in the US are going to be all Slingshot 11 based, and either big AMD CPUs or GPUs, followed by kind of the next generation Intel ones. So we do have some preliminary results gathered on like an exascale test bed, I think up to 128 cores, and roughly we see kind of double the performance of what we saw on this HPE Apollo system. And all that to say, I think we have good performance portability to various Cray and HPE networks as well as InfiniBand, and we have some older results that show decent performance on Ethernet, although we still have some more work to do there. So wrapping up then, I'm not going to go through all of this, but there's some additional Chapel resources that are linked here if you want to learn more. And in particular, if you want to get kind of a better review of Chapel's history or where things stand, or even the use cases in Arcuda and Champs, there is information here. And then just kind of the high level summary here is, Chapel is a modern programming language designed for productive parallel computing at scale. And I think we've seen a lot of success with that goal, and we've seen a lot of success with recent users like Champs and Arcuda who have benefited from these for large applications. And though Chapel is PGAS in nature, kind of our ability to avoid traditional SPMD and both synchronous assumptions really enable ease of use. So parallelism is expressed in the source code starting from a single task, like you would have for kind of a commodity mainstream language. Lexical scoping really simplifies PGAS-based communication. And the net result is a far more approachable distributed parallel language. We've seen that aggregators are really important for getting performance and elegant performance and concise and cleanly written code for Arcuda and Bale. And we have performance that rivals and sometimes exceeds that of what we see in kind of really tuned SHMEM implementations. And so we think Chapel's design and language-based nature provide really great optimization opportunities. We've seen that with sort of the asynchronous optimizations and the automatic aggregation. And these are all things that we think make it much easier to program these large HPC systems. And for all of this aggregation, the ability to create a lot of tasks is really what allows us to have good performance. And the ability to create a lot of these tasks that can then hide latency with that effective task switching is really important. And that's all I have for you today. thanks for your attention, and I think we should have some time for some questions.
All right.